Today we shall look at the effect of the flow of corrosive environment on the corrosion of metals. So far what we discussed was related to the environment being very static, and in several cases, at least in industry, the environment need not be static. The environment, there is a flow. There are so many complex flow conditions that exist in the industrial scenario. The corrosion of metals are different if the environment flows in relation to the metallic structures. So this topic assumes very greater importance. So we will discuss in detail what are the kinds of flow that affect the metallic structures from the corrosion point of view, what are the mechanisms involved, the factors that control the flow assisted or velocity affected corrosion, and then also we look at the control measures. So here we would say that flow assisted, I am going to separate out like this, and or erosion, cavitation, corrosion. Now as I told you, there can be a relative movement of environment. Please notice that when you say the environment, we talk about not a benign one, it is a corrosive environment. Now let us try to understand what you mean by relative movement first of all. The structures can be static, can be what happens, the environment moves, I would say. Say an example, is a pipeline carrying water, carrying various types of chemicals. Another example could be heat exchangers, right. The structure is static, the environment moves, maybe at different velocity, different pressure, temperature, all this happen. The structure move. Can you give an example? Anybody? You can say ship, but the velocity is not okay. You can say ship. You can talk about an aircraft also, spacecraft. Sure. In fact, the aircraft moves at a very high speed. Other examples, industrially, agitators, right? In a turbine, right? A turbine, the blades. It could be a gas turbine or it could be a hydraulic turbine, a gas engine. Anything else? Impellers, they move. Propellers, they move. So, these are about the two types of structures I would like to say. Okay. Now, let us look at the environment. What is mean by the environment here? Of course, we will talk about the fluids. At least one has to be a fluid. I mean, corrosive environment is a fluid. It could be a single phase or it could be multi-phase. Generally, two phases can happen common, right? Let us say simply a water, sea water. An example, this is sea water plus some sand, right? Can happen. In a thermal power plant, for example, you talk about the steam generators, you may have a gas, steam, you may have water. In a gas turbine, there can be corrosive gases, there can be particles. So, when you say fluid, it is not necessarily a liquid, okay. It can be a corrosive gases, it can be liquid, but the solid is not necessarily a corrosive. In most cases, you do not even consider them as corrosive. Their role is to give an impact. We will see this later, how they can really affect the corrosion of structures. If you look at in the fluid conditions, when the fluid moves, how the corrosion rate of the structure or the metallic structure can change with respect to the velocity. We have seen in somewhere, right, I think the role of velocity on corrosion. Corrosion rate, right? We have seen before. Can anybody recollect? Yeah? Yeah, we talk about a concentration polarization, right? When there is a concentration polarization, when you increase the velocity, the corrosion rate increases. It is simply a diffusion control process actually there. If there is no diffusion control process, the velocity does not play any significant role. You can go back and see your the first part of the course on thermodynamics and kinetics of electrochemical corrosion. If you plot this, something like that, the corrosion rate initially increases gradually like that, a steep increase in corrosion, then again it slopes off like this. That is you see here there is a velocity called a critical velocity. above which the rate of corrosion steeply increases with velocity, right. When you visualize, let us say so a pipeline, suppose visualize it, and if the fluid travels in the pipeline, if the movement of the fluid is parallel to the surface, what do you call that? We call a laminar flow. Right? If the flow rate is increased, what happens now? It is no more parallel to surface, it is going to hit the surface. Okay. What do you call this? Now the laminar flow, turbulent flow, they all depends, this is described by Reynolds number and there are equations, we will not get into that kind of discussion here, okay. But it is enough to understand that the velocity, or I put other way around, the nature of flow decides the kind of corrosion it can happen. The laminar flow or a turbulent flow, that depends on velocity, density, the dimensions of the pipeline, so many factors. So the rate of corrosion over here, the nature of corrosion over here is different from that of over here, can happen. So you can say that in this case, you can divide this something like, this is going to be a turbulent and it is going to be laminar. And major part of the laminar flow, I mean, we can say that can be, the corrosion rate can be controlled by the diffusion processes. If it is essentially corrosion is a diffusion control, right. Some of you would have studied, if you can recollect that, right. If you recollect, if it is a cathodic reaction, so diffusion control, right, this is called IL and the velocity increases. We talked about this, right, in the first part of the class. So it is a diffusion control process and the corrosion can assist, and the mass transport is important. You will see later how the corrosion can get affected, right. Now depending upon the kind of flow conditions exist in a pipeline, the types of corrosion can be broadly classified into 3 types, okay. Nature I call as types of corrosion which are induced by the flow, okay. One is called as flow induced corrosion. This is essentially related to increase in mass transfer. Mass transfer of what? The mass transfer of the corrosion product. How quickly it can get removed from the surface. earlier we talked about the diffusion control process of what? In that case, what is diffusion control there? If you remember, when we said here, what was the mass transfer control here? It is the cathodic species that is mass transfer control. We will see here, in this case it is not necessarily the cathodic species, reduction species mass transfer control. It is oxidized species which are mass transfer control. I will just talk about shown. Next is erosion, corrosion. Here it is mechanical damage, mostly of surface films. So there is an impact, there is a real erosion taking place, right, in the sense of mechanical factor. The other one is a cavitation corrosion. It is majorly mechanical. Corrosion, if I can say, is minor, okay. I put within quotes, okay, is minor. Now we have classified the corrosion occurring on a metal into 3 different categories, primarily because the mechanism of corrosion in all these cases are different. When the mechanisms are different, the solutions are going to be different, okay. So we are not going to apply the same solution in all the cases. Of course, I mean there can be an overlap of properties and the protective measures, but distinctly they are different. You can see that. So now let us look at the first type of thing, that is the flow assisted corrosion. Flow induced or flow assisted, you can call either way actually. What is this flow induced corrosion or flow assisted corrosion? What is this? What does it do? What it does is that the flow that happens in the system, mostly in the pipelines, they assist the solubility of corrosion products. Then reduce film formation and so it can enhance corrosion. It can happen in single or 2-phase conditions. 2-phase, 2-phase flow, I would say. Let me try to explain what we mean by this, all these factors here. The flow assisted corrosion was first a problem were found in thermal power plants. They are found in thermal power plants, and they made a survey in 1997 of 63 power plants, 63 plants, utilities. In all these cases, they found quite an extensive plants suffered the flow assisted or flow induced corrosion. Now in power plants, what do you use? I mean you generate steam, right, and steam is used to run the turbine. So that means you are going to use water. It is essentially a pure water. Okay, so we are not discussing that. Probably in the next course on industrial corrosion control, we will talk about corrosion of boilers and all these steps. The generation of steam means you use pure water. There are certain specifications depending upon the pressure of the boilers. They maintain the pH, they maintain the purity levels, conductivity, and so on and so forth. They normally use steels. Okay. How does the corrosion resistance of the steel occur there? Primarily because by controlling the pH, you can do that. When you do that, they form a film on the surface. See, otherwise you can imagine that steel is, in a typical boiler, the temperature can be about 250 to 280 degrees Celsius, okay, and in economics maybe 130, 140. The temperature of the steel tubes are in this range, and you use water, and it will undergo corrosion, right. See, you know very well, and you have a lot of steel structures here. When rain comes, you see a flash rust. Just a couple of hours, you see it all turning reddish brown. How is it possible for the steel to resist corrosion here? By controlling the environment. That means you change into an alkaline pH, and the film formation becomes a dominant mechanism of corrosion prevention of steel. So that means these oxides are generally a magnetic oxide, right. This is what is the magnetic oxide? Fe3O4 is a magnetic oxide formed, and this oxide prevents the corrosion of steel structures. Now please look at, you have this formation. When does it form? This will form only when the solubility of Fe2 plus and Fe3 plus, right. This constitute Fe2 plus and Fe3 plus, am I right? If the solubility of this one, okay, is less than the concentration of ions, right. So here what happens, you have Fe2 plus and Fe3 plus ions are coming by dissolving. If the concentration exceeds certain limit, they form the precipitate, they form a protective oxide. Please understand this, okay. So that's how generally these metals are prevented. Now if I have a flow, what happens? They swept away these ions from the surface. These ions are not going to get enriched, and so the film formation becomes very low, right. So high velocity, high flow rate means they are, the low concentration of Fe2 plus and Fe3 plus taking place. That means the metals start dissolving more and more, okay, as you increase the velocities. So here that is what it means. Here the velocity increases the dissolution process by sweeping away the corrosion products. that means the film formation becomes very low in that cases. So, that is the primary mechanism of corrosion of steel by flow induced corrosion process. How do they appear? How do they appear? This is the photographs taken on steel pipeline. I mean, you know, superheated heated water. You see the left side has got a single phase flow here, the two phase flow. You can see that the surface is quite rough, okay. Because of the dissolution process, the surface becomes rough. See, they are dissolved in water. Here it is, they call it tiger stripes. It looks like a appearance like a tiger stripes. So they named as tiger stripes. Please understand that these are not a very high magnification. They are lower magnification. They are not microstructures. Okay. So this is the kind of appearance of the surface. They are affected by flow assisted or flow induced corrosion process. Now, these are very important. It occurs in the power plants in several places: boiler, feed water pump, place of occurrence. Feed water pump, tube sheets, tubes in HP heaters, heater drain lines, economizer inlet tubings, piping to economizer heads, deaerated cell. Now, there are several places. I think I just give some illustration that they are important for thermal power plant. Of course, it can happen for nuclear power plant as well, right. So, you have seen now the mechanism of flow assisted corrosion. We have seen the importance of the flow assisted corrosion. Okay. Now, let us look at what are the factors that affect the flow assisted corrosion. Okay. Obviously, you always have a material component, right. You have the environment, conditions, then you have what is called as hydrodynamic conditions. So, people have modeled this actually. In fact, this is one of the serious problems in nuclear power plants. Okay, they have modeled this flow assisted corrosion. The factors that involved are material, seen, the environment, and the hydrodynamic conditions existing in a flowing system. Now in the materials mostly people talk about the chromium content later, the environment, we have the pH, temperature, okay, the oxygen content, and the hydrodynamic condition means it is all related to mass transfer coefficient, right, how the mass is being shifted from the surface to solution. So there are going to be a complex parameters, okay. So if you look at this, it is very interesting now. In a pipeline, the hydrodynamic conditions might change depending upon what? Depending upon the diameter, the velocity, the shape. For example, it is a U bend or maybe it is a elbow, okay. These locations are affected by severely by this flow assisted corrosion, but these are straightforward pH, temperature and oxygen content, and increase in chromium content is supposed to be better from the resistance point of view. Chromium increase in chromium lowers flow assisted corrosion. And I say that if it is more than 1 weight% chromium, there will be no flow assisted corrosion. I do not say no, and it says I would say I think significantly lower. Huh? It does not occur in stainless steel, and stainless steels are not used very extensively, because they are expensive process, materials. So in economizers, many of the units we discussed here, they are not made up of stainless steels. Earlier they made up of simply carbon steel. Now people go for chrome steels. Okay, 1 chromium or even 2, 2/4 chromium kind of, but 1 chromium is quite common. Materials now people use in order to prevent the flow assisted corrosion of metals.
How 1% chromium?
Yeah, it's a good question. You just give me just some time. We'll discuss now. You'll see how this 1% chromium is sufficient enough to form a stable oxide on the surface. Okay. Let's look at the environment now. Okay. First, the temperature. And the velocity. These two are very critical. So plot temperature versus the corrosion rate. You will find like this. And very interestingly, the temperature in this range, these are different velocities, V1, V2, V3 and V4, and V1 smaller than V2, smaller than V3, smaller than V4. When the velocity increases, the flow assisted corrosion increases, but notice here, it increases steeply at this temperature. With temperature it rises and then there is a drop in the corrosion rate. So, it is a very unusual thing that you notice for any corrosion process. It is not same as we discussed earlier, you remember earlier we discussed that effect of temperature on the corrosion rate of water, remember, I think some of you, I said that when you raise the temperature above 85 or so, the corrosion rate of water drops because the oxygen escapes from the surface, right, from the water. In a boiler that does not happen, right, the oxygen cannot escape from that, nor the oxygen is present in this water at all. So, what happens is that essentially if you raise the temperature, what happens to solubility? In some cases the solubility increases, in some cases the solubility decreases. What do you call the solubility called? Have you heard of this? Retrogressive solubility. So, the metal starts precipitating after certain temperatures. So, when you raise the temperature, the ability of the system to precipitate, to form protective film increases. So, the rising temperature increases the kinetics of metal dissolution. Assume that there is no film on the surface. The rise in temperature will only lead to increase in the corrosion rate, am I right? Assume that no film is formed, and if you raise only the temperature, the corrosion rate only will increase with temperature. But, so there are two factors, the rise in temperature increases the corrosion rate, but the rise in temperature also increases the scale forming tendency. So, the corrosion rate starts falling like this. So, you have an optimum value here wherein the corrosion rate is highest and then it starts falling, okay. So, this is a typical of you find in thermal power plants, they are operating for the utilities actually, okay. And this temperature is in the range of, 129 to 149 degrees Celsius for single phase flow, and it is in the range of 149 to 199 degrees Celsius for two phase flow. So, what are the factors that then can control flow assisted corrosion? Velocity, the temperature, right, the pH. Now, all of them should be seen in the light of the ability to form an oxide film or to damage the oxide film. Please look at that, okay. So, those factors which assist the formation of the film will lower the flow assisted corrosion, and those factors which dissolves the film will increase the flow assisted corrosion. So, you do not need chromium to form a passive film in steel. How does the film is formed? The film is formed by maintaining the pH. The pH is a primary thing for that. So, the role of chromium is just to assist the film formation. So, it is not going to be a pure chromium rich passive film that you see in stainless steels, okay. Here the film will be having rich in iron oxide is Fe3O4, but the chromium assists the formation of a stable Fe3O4. So, the kind of film formed here is not same as the kind of film formed in stainless steels. The chromium is only assisting it. If the pH is not properly maintained, I do not think that chromium will be sufficient to form any film at all actually, okay. So, that is from, you have seen from only from that point of view, and so the 1% chromium is good. Of course, you increase the chromium content, it is even more better, but of course, it cost increases. In industry, every penny is important. You do not want to keep increasing the MOC better materials, because that is going to cost more. Okay. Now, what else can improve the film formation, interestingly, is the role of dissolved oxygen. Okay. So, whatever you discussed is supported by this. Dissolved oxygen content, DO content, versus the corrosion rate. Now, okay. So, this is called as polished surface, this is pre-filmed. Please notice that generally the boilers are passivated, there is called a treatment called passivation treatment people do, they call alkali treatment in order to form the film. Okay. If you have a film here, it is even better. So, please notice that the oxygen content helps to decrease corrosion rate, because the oxygen will, what does oxygen do? It stabilizes it increases the corrosion rate, no doubt, but if it increases the corrosion rate beyond certain level, it will enriches the metallic ions on the surface and it forms a film. It is very similar to critical current density, right? When you reach the critical current density, at that point of time, you have more metallic ions, then the passive film starts forming. So, you need a critical amount of metal ion concentration on the surface in order to form the protective oxide film. So, the oxygen content, it does help to do this. This means, it is very interesting here, the corrosion control in this case is done by injecting some oxygen content. In the boilers, okay, and it's about 50 ppb. Please look at it is not ppm level. This is 50 ppb levels. So they lower the flow assisted corrosion. Okay. So we will not get into discussion of the mechanism of that. There are a lot of papers available. Those who are interested, you can read. Please notice, this water treatment is not common for all the boilers. The normal boilers we talk about, they do not use this, but now we use boilers such as, hope you people might be aware of this, supercritical boilers. They give this treatment, they give this called as oxygenated treatment. In order to reduce the flow assisted corrosion. So, I just summarize now what we have seen so far, so that you have some clarity. You have flow assisted corrosion. What are the factors that affect flow assisted corrosion? It is a material, the environment involved, and of course the flow conditions or hydrodynamic conditions. The mechanism here is what? the flow assists what? Simply the electrochemical dissolution process. Notice no mechanical damage. It is simply that the flow conditions help to sweep away the corrosion products, and so the corrosion is increasing. They do not allow the film formation or lowers the film formation on the surface. How do you control this? Control measures: chromium alloyed steel used. Maintaining the optimum pH. Very important thing, the design, right? Why you say design? The hydrodynamic conditions existing on the surface depend upon flow conditions, right? So it could change. If you are going to have a sharp bends, you are going to have more flow assisted corrosion. If you avoid that, it may reduce. If reduce the velocity, then also the erosion, not erosion, corrosion, flow assisted corrosion would decrease. So the design of the system also is equally important. And of course the corrosion allowance, you do not want that as the primary way of preventing it, but that still is, we are not going to totally eliminate flow assisted corrosion, but incorporate the flow assisted corrosion rates in the design, especially in a unit, some places inlets for example, or maybe the bends, elbows, you should incorporate the corrosion allowance to lower the flow assisted corrosion. Move on to next topic, which is erosion corrosion. Let us straight away bring out the difference between erosion corrosion and the flow assisted corrosion, okay. Here no mechanical damage, right. In the erosion corrosion, mechanical damage is predominant. It happens very widely across several industries. The flow assisted corrosion mainly I would say related to the power plants, either it is a nuclear or fossil fired boiler, power plants, okay. So you see this in almost the pipelines, the locations, I would say the locations or where you see them, the erosion corrosion are the pipelines, especially on the bends and elbows. See this, you can see that them in the heat exchangers, especially in the inlets. You see them in the reaction vessels. You will see the agitators, grinders for example. See in the mining industry, that grinding is very common, right, and sometimes even this the ore is transported as a slurry along the pipelines. So you see huge amount of erosion corrosion taking place in the pipelines. Again you will see that impellers and gas turbines and hydraulic turbines, okay, nozzles, they are all quite common examples of erosion corrosion taking place. It is an example of the erosion corrosion. Please do not use the term flow assisted corrosion here, it is now erosion corrosion. What you see is this is a reactor vessel, reactor vessel is a wall, actually it is a wall. Actually there is a reactor, there is the inlet here, this is the inlet for this is actually the sulfonic acid. So reaction vessel here, this is a kind of autoclave, you want to call it, reactor you call it. Through this the sulfuric acid is pumped. This is the surface of the reactor, the sulfuric acid travels like this, okay. You can see the mark, you can see the marking here, severe corrosion here taking place, right. Next to that there is not much of a corrosion for two reasons of course, one is the velocity, see here. The second is then the sulfuric acid get diluted, right, I mean the sulfuric acid get diluted, the corrosion rate of the sulfuric acid also comes down, sulfonic acid here. So you can also see some kind of flow patterns. Are you able to see this here? I hope you are able to see this flow pattern here, right. So these these are all having specific features to show that there is certain amount of uniqueness in the way the metal gets damaged. They call it fingerprints, okay. This reactor did not even last for about 6 months. Within 6 months, the reactor starts leaking. Yes. This is the earlier one was a stainless steel. It's a stainless steel. What you see in here, it's not a carbon steel. It's a stainless steel. This one is a copper nickel alloy. It is copper 10% nickel, and this is a tube for an heat exchanger. In the tube the seawater was flowing. Look at this, the velocity was hardly about 1 meter per second was the velocity. The external, I mean on the shell side, the process fluid, it essentially is hydrocarbon. You do not see any corrosion on the shell side. I hope you can see the marks here, right? You see the marks here, okay, the marks, and I hope you can able to see some mark here also, right? This is an inlet, the inlet of a heat exchanger. So very interesting, and there are several tubes in the heat exchanger. within about few months of commissioning, some tubes started leaking, few months. Okay. It was in a refinery located in Mumbai. So they changed the tubes. Within another 1 month, the heat exchanger started leaking again, and they again changed the tubes. Almost every month they had to shut down the plant. See, when you shut down the plant, because this is a critical heat exchanger, if this exchanger does not operate, then the whole refinery has to shut down. If you shut down the refinery for a day, it just runs in crores of rupees. It's not just lakhs, it's crores of rupees. The material is not very expensive compared to the production loss. See this. They were using seawater, and seawater stainless steel will have some problem because they may pitting corrosion, or you may have Crevice corrosion, and copper nickel alloy is supposed to be good because they do not pit and all, right. And copper nickel is certainly better from the point of view of what you call as de-alloying as compared to brass. We have seen it, you seen yesterday, right. A little bit of discoloration, you can see this little bit of green color that has happened because of the nickel dissolution process. But nevertheless, 1 meter per second is hardly a velocity and is failing so frequently. So that was one of the problem. We will probably see what could be the problem in subsequent discussion. When we start analyzing the erosion corrosion, then we come back to this problem and see what was the real reason for the erosion corrosion of this particular heat exchanger. Now, what I was trying to say was the inlet of the heat exchangers generally undergo the erosion corrosion. In fact, that is termed as inlet corrosion. So, when there is a turbulent, it mechanically damages, you see, it removes mechanically, okay. But then what is the difference between erosion and erosion corrosion? So, I give an example. Suppose there is a pipeline and you are passing, let us say, nitrogen gas in the pipeline, maybe there are certain solid particles, okay, and the tube gets damaged. So, it is a purely erosion damage. You put a bit of moisture in the system and you say that gas is no more dry, the solid particles are no more dry, you just have some water. Now it becomes erosion corrosion. Why? Because you have a corrosion component coming over here. So erosion corrosion, it's a conjoint action of the mechanical erosion factor and assisted by the corrosion factor. So when you talk about erosion corrosion, then we look at the mechanical property of the material as well as the corrosion property of the materials, okay. So that makes a difference. In the flow assisted corrosion, we never talked about mechanical property of the materials, we talked about the film formation, film stability. That is why I said the mechanism are different, and so the way you prevent corrosion also going to be different here. So what are the factors controlling erosion corrosion or affecting erosion corrosion? Here also we talk about the surface films. They are important. Talk about velocity, impingement, turbulence, etc. They are related to the physical state of the environment, velocity, impingement, turbulence. They are not talking about the chemical state of it, right? We are not talking about the pH of that, corrosiveness of that. Is a physical state of the environment, okay. Metallurgy of this. The metallurgy of the alloy will also decide the surface films, it is not necessarily they are independent, okay. But metallurgy here we generally mean in terms of the other mechanical properties such as hardness, toughness, all kind of stuffs. So let us look at the surface films. Let us take the first one. Please notice the film offers a barrier for corrosion, it also takes the impact. Takes impact of the environment. Right. So what should be the property of the film or properties of the film which can provide a better erosion, corrosion resistance? What are the properties? It should be, the film should be one, it should be hard, isn't it? Then what happens? It should be adherent. 2, 3, what happens? It should be resilient, right? And if you want it more explicitly, be less brittle, right? What more? Should be dense and less porous. So those alloying elements that added to the alloy that can promote all these properties will ensure that the alloy has a better resistance against erosion, corrosion problems, okay. So these are the important things, that is the guiding factor for alloy development also, right. So please notice, it is not necessarily a very thick film, sometimes thick films can be a problem, isn't it? A thick film, generally the oxide films are brittle compared to the metal. When the film becomes thicker and thicker, what happens to the resilience? It becomes very bad. When the film is thin, it is more resilient against any kind of elastic deformation, right. And in erosion corrosion, you are not going to get into too high impact. In cavitation it does happen. So you are talking about a resilient within the elastic limit, most of the deformation would occur in erosion corrosion, okay. Let us look at some examples of the surface film formation happen. The surface film formation would also depend upon the nature of environment. It is not just only metal also, okay. Suppose I take a stainless steel, I have a reducing environment, what happens to the film forming tendency of a stainless steel? Decreases, right, because you need oxidizing conditions. That could be seen very well in the case of, let us say, type 316 stainless steels, corrosion in ferrous sulfate plus sulfuric acid slurry. Please notice ferrous sulfate is reducing condition, not oxidizing condition. Ferric sulfate is oxidizing condition. If you use 316 stainless steels and if you can look at the corrosion rate, again with respect to temperatures, the corrosion rate of that somewhere about 5000 mpy, something like that. In the static conditions, ferrous sulfate plus sulfuric acid slurry in the static condition, this is not flow condition. Where if you increase the velocity, or something like that. So I think it's about around about 3 meters per second rate is going. So it's going very high corrosion rate, steeply also changes with respect to temperatures. But you add 316 stainless steel and add some copper to that, the corrosion rate, copper added. So when you add a copper to stainless steel, the film forming tendency becomes very high. In fact, if you look at the material selection for sulfuric acid applications, the stainless steels have copper in it. So copper helps to form stable passive film. So there is a significant drop in the corrosion rate, and these copper additions are all what? They are all in terms of what, 0.01 to 0.02 weight percent, not a very large amount of copper content. It can happen. Similarly, and what people have seen, seawater a copper, a brass. The copper forms cuprous chloride and it forms cuprous oxide in deaerated seawater. Okay, and cuprous oxide is more stable. So what happens? So copper zinc is better. So what we are trying to say is that the nature of the film that forms on the material decides the erosion, largely the erosion corrosion resistance of the material. The other example is steel in pure water. It's okay, where they studied the pH at 50 degrees Celsius and the velocity is about 39 feet per second is the velocity here. Okay. corrosion rate. And this is around about 6, about 10 pH. Now, the reduction in the corrosion rate, both the places are largely related to ferrous hydroxide and ferric hydroxide formation. Here from granular Fe3O4 oxide formation. Okay. Again, there are a lot of internal stresses. So, the point that we need to emphasize here is that the nature of oxide forming on the metal surface bears a significant influence on the erosion, corrosion of metals. So, let us stop our discussion for the time being.